This is the EdExcel A-Level Further Maths Paper 2, covering the core pure content, and it's from the June 2022 series. Question number 1. A student was asked to answer the following. For the complex numbers z1 equals 3 minus 3i and z2 equaling root 3 plus I, find the value of the argument of z1 over z2, and the student's attempt is shown below. For line 1, to work out the argument of z1, they did the inverse tangent of 3 over 3, which is pi over 4. For line 2, to work out the argument of z2, they did the inverse tangent of 1 over root 3, which is pi over 6. For line 3, to work out the argument of z1 over z2, they did the argument of z1 divided by the argument of z2, and for line 4, substituting in their values for the argument of z1 and z2, they did pi over 4 divided by pi over 6, which they got as 3 over 2. Now, the student made errors in line 1 and line 3. We have to correct the error that the student made in line 1 and line 3 for part A of the question. Well, line 1 should be, if we take a look at what z1 is, the argument of z1 equals the inverse tangent of negative 3 divided by 3, because the imaginary part is negative 3. And so working this out, the argument of z1 is equal to negative pi over 4. Now, line 3 should be, well, if we want to work out the argument of z1 over z2, the argument of z1 over z2 is equal to the argument of z1 subtract the argument of z2. And then for part B, we have to write down the correct value of the argument of z1 over z2. Well, for part B, now that we know what line 3 should be, we can substitute in the value of the argument of z1. We know the value of the argument of z2, so the argument of z1 over z2, that will equal minus pi over 4 subtract pi over 6. And if we work this out, we end up with minus 5 pi over 12. And so the argument of z1 over z2 is minus 5 pi over 12. Question number 2. A college offers only 3 courses: construction, design and hospitality. Each student enrolls on just one of these courses. In 2019, there were a total of 1,110 students at this college. There were 370 more students enrolled on construction than hospitality. In 2020, the number of students enrolled on construction increased by 1.25%, design increased by 2.5%, and hospitality decreased by 2%. in 2020, the total number of students at the college increased by 0.27% to two significant figures. For Part A, for the first part, we have to define for each course a variable for the number of students enrolled on that course in 2019. So, for the first part of Part A, we will let x be the number of students enrolled on construction in 2019. We will let y be the number of students enrolled on design in 2019. And we will let z be the number of students enrolled on hospitality in 2019. Then for the next part, using your variables from the first part of Part A, we have to write down three equations that model this situation. So, what we know in 2019, there was a total of 1,110 students at this college. So what this means then is x plus y plus z equals 1,110. So we know that x plus y plus z is equal to 1,110. We also know that there were 370 students who enrolled on construction than hospitality, which means x is equal to 370 plus z, and if we rearrange so the variables are on one side, we have x subtract z, which is equal to 370. And if we take a look at what else we know from the question, we know that in 2020, construction increased by 1.25%. So if construction increased by 1.25%, and we also know that design increased by 2.5% and hospitality decreased by 2%, then we have 1.025x, rather 1.0125x plus 1.025y plus 0.98z. So this is considering the increases. We know that this will equal, well, we know that in 2020 that the number of students increased by 0.27%. So in 2020, the total number of students increased by 0.27%, which means this is equal to 1.0027 multiplied by x plus y plus z. And this amount here is the amount in 2020. And so if we rearrange, we have, in terms of the x's, 1.0125 subtract 1.0027 So that is 0.0098 x. Then in terms of the y's, we've got 1.025 subtract 1.0027. So that is the same as 0.223y. And then in terms of the z's, we've got 0.98 subtract 1.0027. So that's minus 0.0027 z. And this is equal to 0. And so if we attempt to simplify this, we can multiply by 10,000, leaving us with 98x plus 223y subtract 227z. That's equal to 0. So we have formed equations based upon this situation. And then for part B, by forming and solving a matrix equation, we have to determine how many students were enrolled on each of the 3 courses in 2019. So in other words, we need to find x, we need to find y, and we need to find z. So if we were to form matrix equations based upon the information given, in terms of the x's, we've got 1x for this equation, 1x for this equation, and 98 for this equation. And then for the y's, we've got 1 for this equation, 0 for this equation, and 223 for this equation. So we've got 1, 0, and 223. And in terms of the z's, we've got 1z here, minus 1z here, and minus 227 here. So we've got 1, minus 1, minus 227. And we multiply this by the vector x, y, z. And this would equal, well, we've got 1110, 370, and 0. And so what we need to do is find out what x, y, and z are. So we have x, y, z equaling the inverse of this matrix multiplied by the vector 1110, 370, 0. To find x, y, z, if we go to the matrix sub-menu, we can define matrix A, 3 rows, 3 columns, then we type in the components of our matrix, and then we want to take the inverse of that matrix, so we load up matrix A, and then we want the inverse of this. So we have 223 over 575, 129 over 575, 223 over 575, 18 over 23, minus 13 over 23, minus 5 over 23, minus 1 over 575, 2 over 575, and minus 1 over 575. And then this will be multiplied by this vector here. So now, if we define a matrix B, say, with 3 rows, 1 column, then we have our inverse of this matrix, which we've worked out, and then we want to multiply this by matrix B. So we have x, y, z equaling 720, 40, and 350. And so what can we conclude from this then? We have 720 of the students enrolled on construction in 2019, 40 of the students enrolled on design in 2019, and 350 of the students enrolled on hospitality in 2019. Question number 3. We are given that matrix M is 3A01, where A is a constant, and for part A we have to prove by mathematical induction for n belonging to a set of natural numbers that m raised to the n is equal to 3 to the n a over 2 multiplied by 3 to the n minus 1, 0, and 1. Our goal is to show m to the k plus 1 is equal to 3 to the k plus 1, 0, a over 2 multiplied by 3 to the k plus 1 minus 1, and 1. So, with our first step in a proof by induction question, we see what happens when n is equal to 1. And when n is equal to 1, m to the 1 is equal to 3, 0, a over 2 multiplied by 3 to the 1 minus 1, 1. And so if we work this out, we have 3, 0. Now here we have 3 to the 1, which is 3. Subtract 1, that's 2. And I'm multiplying 2 by a over 2, so that's just a. And then we have 1. And m to the 1 is therefore equal to m, which is what we see here. So the statement is true for n equals 1. Our next step is to assume the result is true for n equals k plus 1. In other words, we assume m to the k is equal to 3 to the k, 0, a over 2 multiplied by 3 to the k minus 1, 1. We will now try for n equals k plus 1. In other words, we replace n with k plus 1 with m, which means we have m to the k plus 1, and using the laws of indices, this is the same as m to the k times m to the 1. Now m to the k, using our assumption step here, we have 3 to the k, a over 2 times 3 to the k minus 1, 0 and 1. And then we multiply this by m to the 1. Now m to the 1 we worked out over here as 3a, 0, 1. And so if we use matrix multiplication, we have 3 to the k multiplied by 3 plus a over 2 multiplied by 3 to the k minus 1 times 0. Then we have 0 times by 3 plus 1 times by 0. And then we have 3 to the k times by a plus a over 2 times 3 to the k minus 1 times by 1. And then we have 0 times by a plus 1 times by 1. So now let's attempt to simplify all this. We have 3 to the k times by 3, so that is the same as 3 to the k plus 1, because 3 is the same as 3 to the 1. Then here we've got 0 plus 0, which is 0. And then here we have 3 to the k times by a plus a over 2 multiplied by 3 to the k minus 1. And here we've got 0 plus 1, which is just 1. So now let's try to simplify this even further. The way we can simplify this even further, well, we still have 3 to the k plus 1 and a 0. And here we have 3 to the k times by a. And if I multiply the a over 2 into this bracket, then we are adding on a over 2 times by 3 to the k, and then we subtract a over 2. And then here we have 1. So we've got 3 to the k plus 1, 0. And here, if I factorize out an a over 2, then inside the bracket we have 2 multiplied by 3 to the k plus another 3 to the k, subtract 1. Notice a over 2 times 2 times 3 to the k is just 3 to the k times a, and a over 2 times 3 to the k is a over 2 times 3 to the k, and a over 2 times negative 1 is negative a over 2, and then we've got this 1 here. So we have 3 to the k plus 1, 0, and here we have a over 2 on the outside, and inside we've got 2 times 3 to the k plus another 3 to the k, so that's 3 times 3 to the k, and then we've got the minus 1, and then we've got the 1 here. And we know that 3 times 3 to the k is just 3 to the k plus 1. So we have 3 to the k plus 1, 0, a over 2 times 3 to the k plus 1 minus 1, and then 1. And if we take a look at what we wanted to show with our goal, that's exactly what we've ended up with. So, if the statement is true for n equals k, then we've just shown that it's true for n equals k plus 1. And as the statement is true for n equals 1, that means it's true for n equals 1, n equals 2, n equals 3, etc. And so therefore, it's true for all natural numbers of n. For part B of the question, triangle T has vertices A, B and C. Triangle T is transformed to triangle T dash by the transformation represented by m to the n, where n belongs to a set of natural numbers. And given that triangle T has an area of 5 cm squared and triangle T dash has an area of 1215 cm squared, and the vertex A, 2 minus 2, is transformed to the vertex A dash, 123 minus 2, we have to determine the value of n and the value of A. Now, if we have a series of transformations, what's happening is we take our vertex A, transform it by m to the n, and then we end up with the vertex A dash. So, for part B of the question, we have the matrix m to the n, which is our transformation matrix. So we have 3 to the n, 0, a over 2 multiplied by 3 to the n minus 1, 1. And we are applying this transformation to the vertex 2 minus 2. And what we end up with is 123 minus 2. So, we have 3 to the n multiplied by 2 plus, well, here we'd have negative 2 multiplied by a over 2 times 3 to the n minus 1, and that's equal to 123. So we have 3 to the n times 2, subtract, well here we've got negative 2 times by a over 2, so that's just negative a, and then we have 3 to the n minus 1 equaling 123. Now we'll call this equation 1 for now. We can't do much with it now. What we also know from the question is we've got triangle T, which has an area of 5 centimeters squared, and triangle T dash, which has an area of 1215 centimeters squared. And if we find the determinant of our transformation matrix, in this case m to the n, that will tell us the area scale factor, and we can also find the area scale factor by dividing 1215 by 5. So if we have the determinant of m to the n, then we have 3 to the n, 0, a over 2 multiplied by 3 to the n minus 1, 1. We want the determinant of this matrix. So if we work out the determinant, we have 3 to the n times by 1, subtract 0 multiplied by a over 2 multiplied by 3 to the n minus 1. So the determinant of m to the n is equal to 3 to the n. And so, recognizing that the determinant of m is equal to the area scale factor, we have 3 to the n equals 1215 divided by 5. The determinant of m to the n represents the area scale factor. So we have 3 to the n equaling 243, which means n is equal to log base 3 of 243. So working this out, we get 5. So we have n equals 5. And now if we use equation 1, so using equation 1 then, what we would have is 3 to the 5 times 2, subtract a multiplied by 3 to the 5 minus 1 equals 123. So we have 486 subtract, well here we have 242a, and that's equal to 123. And so what we can conclude from here then is a equals 3 over 2. Question number 4. For the first part, given that z1 equals 6e to the pi I over 3 and z2 equals 6 root 3 e to the 5 pi I over 6, we have to show that z1 plus z2 equals 12 e to the 2 pi I over 3. For the first part of the question, we are given that z1 equals 6 e to the pi I over 3. Now we can find out what this is equivalent to. This will be equivalent to 6 multiplied by cos of pi over 3 plus I sine of pi over 3. And knowing what z1 is, well, we have the result here which we can enter into the calculator in complex mode. We've got 6 multiplied by the cosine of pi over 3 plus I times by the sine of pi over 3. And it turns out z1 is equal to 3 plus 3 root 3 I. Similarly, for z2, that's equal to 6 times the square root of 3 times e to the 5 pi I over 6. And so we can rewrite this result as 6 root 3 multiplied by the cosine of 5 pi over 6 plus I times by sine of 5 pi over 6. So we can work this out, entering this result into the calculator. So if we do that, we've got 6 times the square root of 3 times by the cosine of 5 pi over 6 plus I sine of 5 pi over 6. And if we work this out, it turns out we get minus 9 plus 3 times the square root of 3 I. Now, in this question, what we want to do is show that z1 plus z2 equals 12 e to the 2 pi I over 3. So, if we begin by working out what z1 plus z2 is, we have z1, which is 3 plus 3 root 3 I plus z2, which is minus 9 plus 3 root 3 I. And so therefore z1 plus z2 is equal to minus 6 plus 6 root 3 I. What we can now do is find the modulus of z1 plus z2 and the argument of z1 plus z2. So, if we find the modulus of z1 plus z2, that's equal to, well, we have minus 6 squared plus 6 times the square root of 3 squared, then square rooted. So if we work this out, we have the square root of minus 6 squared plus 6 root 3 squared, and it turns out the modulus is 12. We can now work out the argument of z1 plus z2. The argument of z1 plus z2, that's equal to, well, if z1 plus z2 is equal to minus 6 plus 6 root 3I, on our calculator, if we change the complex setting to r theta, notice this symbol appears on the top, and then if we type in minus 6 plus 6 root 3 I, it turns out our modulus is 12 and our argument is 2 pi over 3. And to find this argument of 2 pi over 3, we can do pi subtract the argument of 6 root 3 over 6, which is 2 pi over 3. Rather, here we've got the inverse tangent of this, which is 2 pi over 3. So, confirming that, we've got pi subtract the inverse tangent of 6 root 3 over 6, which is indeed 2 pi over 3. And so what we can conclude from this then is z1 plus z2 equals 12 e to the 2 pi I over 3. And that is exactly what we wanted to show. For the next part, given that the argument of z minus 5 is equal to 2 pi over 3, we have to determine the least value of the mod of z as z varies. Well, here is a diagram. We've got the argument of z minus 5 equaling 2 pi over 3, that's a half line, which starts from the point 5, 0. And what we need to do in this question is determine the least value of the mod of z as z varies. And what that refers to is this distance of this line here, which is perpendicular to this half line. And so let's call that least distance d. So the least value of the mod of z as z varies, that is given by d over here. Now, if I call this line L1 And if I call this line L2, what we can do is find out the equation for L1, find out the equation for L2, and find out where they intersect. We can then use the distance formula to find out the least distance, d. So, to find out what the equation of line L1 is, first of all, we need the gradient of L1. And the gradient of L1 is equal to the tangent of 2 pi over 3. So if we work out what this is, the tangent of 2 pi over 3, that's negative root 3. So the gradient of L1 is negative root 3. And if it passes through the point 5, 0, that means L1 would have equation y minus 0, so that's just y, equals negative root 3 multiplied by x minus 5. So this is what the equation of L1 is. We can now find the equation of L2. First of all, we need the gradient of L2. The gradient of L2 is equal to the negative reciprocal of negative root 3. So we have minus 1 over minus root 3, which is 1 over root 3. And because L2 passes through the origin, we can therefore conclude the equation of line L2 is y equals x over the square root of 3. So let's call this equation 1 and this equation 2. Now let's just add this to the diagram. We have L2 with equation y equals x over square root 3. Now, what we need to do before anything else is find out where L1 and L2 intersect. And we know that they intersect at this point over here. And we need to find the coordinates of this point. We can do that by solving equation 1 and 2 simultaneously. So if we set equation 1 and 2 equal to each other, we have equation 1, which is minus root 3 times x minus 5. This is equal to x over the square root of 3. And if I multiply through by root 3, then negative root 3 times root 3, that's just 3. So I've got 3 times by x minus 5 equals x. And then I've got minus 3x plus 15 equals x. 4x is 15, which means x is equal to 15 over 4. And knowing what x is, we can now find out what y is by substituting into equation 2. So, with x equaling 15 over 4, that would imply that y is equal to 15 over 4 times the square root of 3. And if I attempt to rationalize, we end up with 15 root 3 over 4, rather 15 root 3 over 2. Oh, this is just 4. So, if I add those coordinates in, I've got my x coordinate 15 over 4, and our y coordinate, which is 5 root 3 over 4. So, we want the distance from the origin to this point here. So, the distance d then is equal to 15 over 4 squared plus 5 root 3 over 4 squared, then square rooted. So if I work out what this is, I've got 15 over 4 squared plus 5 root 3 over 4 squared, and it turns out the distance is 5 root 3 over 2. Question number 5 for part A. We are given that y is equal to the arcsine of x, where x is in between minus 1 and 1. With this, we have to show that dy over dx is equal to 1 over the square root of 1 minus x squared. So, for part A, we begin with y equaling the inverse sine of x, where x is in between minus 1 and 1. And at this point, we can take the sine of both sides. The sine of the inverse sine of x is just x, and this will equal to the sine of y. And at this point, we can find out what dx over dy is. Differentiating sine y with respect to y, we end up with cos y. And recognizing that cos y is equal to the square root of 1 minus sine squared y, we have 1 minus sine squared y, then square rooted. And we know that sine y is equal to x, so sine squared y will equal x squared, and therefore dx over dy is 1 minus x squared square rooted. And so therefore dy over dx is equal to 1 over 1 minus x squared square rooted. Now for part B, we are given that f of x is equal to the arc sine of e to the x, where x is less than or equal to 0. We have to prove that f of x has no stationary points. Well, if we think about how f of x is similar to y, instead of us having an x, we have an e to the x instead. Now because we are concerned with stationary points, that suggests to us we need to differentiate f of x. And we can use the result in part A to help us differentiate f of x. And so, for part B of the question, if we have f of x equaling the arc sine of e to the x, that means f dash of x through the chain rule is equal to e to the x multiplied by 1 over 1 minus e to the x squared. And that's just using the results from the chain rule. And so if we tidy this up, what we end up with is e to the x divided by 1 minus e to the 2x square rooted. So, if we have f dash of x equaling 0, because we are concerned with stationary points, that would mean that e to the x over the square root of 1 minus e to the 2x is equal to 0. And therefore, we have e to the x equaling 0. Now, can we solve for x at this point? Well, there are no values of x which make e to the x equal to 0, so e to the x does not equal 0. And this is true for all real values of x. And what we can conclude from this then, f of x has no stationary points. Question number 6. The cubic equation 4x cubed plus px squared minus 14x plus q equals 0, and p and q are real positive constants, and this equation has roots alpha, beta and gamma. We are given that alpha squared plus beta squared plus gamma squared is equal to 16, and with this we have to show that p is equal to 12. Now, we begin this question with our cubic equation 4x cubed plus px squared minus 14x plus q equals 0. And if I divide through by 4, that would imply x cubed plus p over 4 p over 4 x squared minus 14 over 4, which is the same as 7 over 2 x plus q over 4 is equal to 0. And from this, we can see then that alpha plus beta plus gamma is equal to minus p over 4. We can see alpha beta plus beta gamma plus alpha gamma, or alpha gamma, is equal to minus 7 over 2. And what we can also see is alpha beta gamma is equal to minus q over 4. And knowing that, if we want to find out what alpha squared plus beta squared plus gamma squared is usually, what we would do here, well, if I have alpha squared plus beta squared plus gamma squared equals, well, I would have here alpha plus beta plus gamma squared minus 2 multiplied by alpha beta plus beta gamma plus alpha gamma. And if I substitute in everything I know, well, I know that alpha squared plus beta squared plus gamma squared, that's 16. So I've got 16 equals, now here we have alpha plus beta plus gamma, so that is negative p over 4 squared, subtract 2 multiplied by, well, here if I've got alpha beta plus beta gamma plus alpha gamma, that is negative 7 over 2. So let's try to simplify all of this. What we have here is 16 equals p squared over 16, and then here we've got minus 2 times by minus 7 over 2, so that's positive 7. And if we do 16 take away 7, that's 9. And if I multiply that by 16, it turns out 144 is equal to p squared, and therefore p is equal to positive 12 only, and that's because p is greater than 0. And that's what we were told in the question, p is a real positive constant. And therefore, knowing what p is, we can therefore conclude we have 4x cubed plus 12x squared minus 14x plus q equals 0. And now for part B, we are given that 1 over alpha plus 1 over beta plus 1 over gamma is equal to 14 over 3, and with this we have to determine the value of q. Well, before we do anything else, let's divide this equation by 4, leaving me with x cubed plus 3x squared minus 7 over 2x plus q over 4 equals 0. And then for part B, well, if we have 1 over alpha plus 1 over beta plus 1 over gamma, well, let's just write that out. We have 1 over alpha plus 1 over beta plus 1 over gamma. If we were to work out what that is equivalent to, that's equivalent to alpha beta plus beta gamma plus alpha gamma divided by alpha beta gamma. And so, knowing that 1 over alpha plus 1 over beta plus 1 over gamma is 14 over 3, then what we have then is 14 over 3 equaling, well, we have here negative 7 over 2 divided by alpha beta gamma, which is negative q over 4. So what we need to do now is find out what q is. So on the right hand side we have 14 over q, and that's equal to 14 over 3. And what we can conclude from here then is q is equal to 3. And so therefore, for our cubic equation, we have 4x cubed plus 12x squared minus 14x plus 3 equals 0. Now, part C, without solving the cubic equation, we have to determine the value of alpha minus 1 times beta minus 1 times gamma minus 1. Now, if we compare our cubic equation with what we have here, well, for our cubic equation we had roots alpha, beta and gamma. Now, what we have now is a new cubic equation with roots alpha minus 1, beta minus 1 and gamma minus 1. And what we can do is use a substitution to help find a new cubic equation. So, because we have roots alpha minus 1, beta minus 1 and gamma minus 1, we can therefore say for part C of the question, our substitution will be of the form y equals x minus 1, which means that x is equal to y plus 1. And what we will do with this is we will replace the x with y plus 1 and form a new cubic equation. So, we have 4 multiplied by y plus 1 cubed plus 12 multiplied by y plus 1 squared minus 14 times by y plus 1 plus 3 equals 0. And this cubic equation this has roots alpha minus 1, beta minus 1, and gamma minus 1. Now, we made the substitution y equals x minus 1 because the roots are of this form here. So, to determine the product of the roots alpha minus 1 times beta minus 1 times gamma minus 1, let's first of all expand and simplify. So, we have 4 multiplied by, well, cubing y plus 1, we have y cubed plus 3y squared plus 3y plus 1, squaring y plus 1, we end up with y squared plus 2y plus 1, then we subtract 14 times y plus 1, we add 3, the result is 0. So let's simplify. In terms of the y cubes, well, I've got 4 times y cubed. Then in terms of the y squared, I've got 4 times by 3y squared, and then I've got another 12y squared. So that will give us 24y squared. And then I've got 4 times by 3y plus 12 times by 2y minus 14y, so that will be 22y, and then I've got 4 times by 1, 12 times by 1, minus 14 times 1, and then the 3, that's 5. So I've got 4y cubed plus 24y squared plus 22y plus 5 equals 0. And if I divide through by 4, I've got y cubed plus 6y squared plus 11 over 2y plus 5 over 4 equals 0. And so, if we want to find the product of the roots will be alpha minus 1 times beta minus 1 times gamma minus 1, and that will equal negative 5 over 4. Question number 7. Figure 1 shows a sketch of the curve C with equation r equals 1 plus tan theta, where theta is in between 0 and pi over 3. Figure 1 also shows the tangent to C at the point A. This tangent is perpendicular to the initial line, and we have to use differentiation to prove that the polar coordinates of A are 2 pi over 4. Well, we've got this polar equation, r equals 1 plus tan theta. And so, for part A, at the point A, dx over d theta will equal 0 because it's parallel to the initial line. Now, if we have dx over d theta equaling 0, what this is the same as is differentiating r cos theta with respect to theta and setting the result equal to 0. Now, we know what r is, that's 1 plus tan theta, so we can replace the r here with 1 plus tan theta. If we make a quick note, r cos theta that's the same as 1 plus tan theta times by cos theta, and ultimately we want to differentiate this result. Now, if I expand out, we would have cos theta plus tan theta times by cos theta. So we've got cos theta plus sin theta over cos theta times by cos theta, which is the same as cos theta plus sin theta. And so what we want to do in this question then is differentiate with respect to theta cos theta plus sin theta. So we will be differentiating cos theta plus sin theta with respect to theta, and then we will set the result equal to 0. And so differentiating cos theta, we end up with minus sin theta, and differentiating sin theta, we end up with cos theta. And if we set this equal to 0, then we have sin theta plus cos theta, rather sin theta equals cos theta, and therefore tan theta will equal 1, and that's if I divide through by cos theta, which means that theta is equal to pi over 4. And knowing what theta is, we can find out what r is. If we find out what r is when theta equals pi over 4, we have 1 plus tan of pi over 4, which is equal to 2. And so the coordinates of A, we've got 2 and pi over 4, and that's in polar form. So A has coordinates 2 and then pi over 4. Now, for part B, the finite region R, shown shaded in figure 4, is bounded by C, the tangent at A, and the initial line. We have to use calculus to show that the exact area of R is equal to 1/2 times 1 minus the natural log of 2. What we can do first of all is find out the area of this triangle. So, for part B, the area of the triangle will be 1/2 times the base times by the height, and in Cartesian that's given by 1/2 times x times y. And so if we convert this to polar, we've got 1/2 multiplied by r cos theta times by r sin theta. So what we've got then is 1/2 r squared sin theta times by cos theta. And sin theta times cos theta, that's a half sine 2 theta. So we've got 1/2 r squared times by 1/2 sine 2 theta. And it turns out we would get 1/4 r squared sine 2 theta. So that's what the area of the triangle is equal to. And knowing what theta is and knowing what r is, we can therefore conclude we have 1/4 times by r squared, so that's 1 plus tan theta squared times by sine 2 theta. So, replacing theta with pi over 4, we've got 1/4 times by 1 plus tan of pi over 4 squared times by 2 times by, right, the sine of 2 times by pi over 4. So let's work this out. If I have the value of theta as pi over 4, I've got 1/4 times by 1 plus the tangent of this times by the sine of 2 times by this rather here I've got 1 plus tan of pi over 4 all squared, and here I've got 2 times by the sine of 2 times by pi over 4. So it turns out here the area of the triangle is 1 unit squared. We can now find out the area bounded by the curve and the line. So to find out what that area is, we can use polar integration. The area is given by a half times by r squared with respect to theta in between our limits, which in our case is 0 and pi over 4. So the area bounded by the curve and the line, we've got 1/2 times the integral from 0 to pi over 4 of r squared, which is 1 plus tan theta squared d theta. So we've got 1/2 times the integral between 0 and pi over 4 of 1 plus 2 tan theta times by plus tan squared theta d theta. And what we can do is write this in an integrable form. We've got the integral from 0 to pi over 4, and then I've got 1 plus 2 times by tan theta, and tan squared, that is the same as sec squared minus 1. d theta. So here we've recognised that tan squared is the same as sec squared minus 1. And the 1 and the minus 1 simplify to 0. So we've got 1/2 times the integral from 0 to pi over 4 of 2 tan theta plus sec squared theta d theta. Now here are the results for integrating sec squared and tan. Integrating sec squared, we end up with tan, and integrating tan, we end up with the natural log of the mod of sec. So, if we work this out, we have 1/2 times by, well, if I integrate 2 tan theta, I would end up with 2 times by the natural log of the mod of sec theta, and if I integrate sec squared, I end up with tan theta. And I need to work this out in between 0 and pi over 4. So, if I substitute in for my upper limit of pi over 4, I've got 1/2 times by, 2 times by the natural log of the mod of sec of pi over 4 plus tan of pi over 4, and then I subtract 1/2 times by 2 times by the natural log of sec of 0 plus tan of 0. So, let's work this out. We have 1/2 times by, well here I've got sec of pi over 4, well that's the same as 1 over the cosine of pi over 4, which is root 2. So I've got 1/2 times by 2 times by the natural log of root 2, and then the tan of pi over 4, that's just going to be 1. Now, I'm going to subtract from this 1/2 times by, well here I've got 2 times by the natural log of, well sec of 0 is just 1, and the tan of 0 is 0. Now the natural log of 1 is just 0, so this term disappears, which means what we have is 1/2 times by 2 times by the natural log of root 2 plus 1. So what we want is the area of R, and to find the area of R, I need to do the area of the triangle, take away the area bounded by the curve and the line. So the shaded area, we've got 1 subtract 1/2 times 2 times the natural log of root 2 plus 1. And now we need to simplify all of this. So I've got 1 subtract 1/2 times by 2 times by the natural log of 2 raised to the power of 1/2, that's the same as square root of 2, plus 1. And if I use the power law of logs, 2 times by 1/2 is just 1, so I've got the natural log of 2 plus 1 inside this bracket. And if I expand the negative 1/2 into the bracket, I've got 1 subtract 1/2 times the natural log of 2 subtract 1/2, leaving me with 1/2 subtract 1/2 times the natural log of 2. And if I factorise out the 1/2, I would have inside the bracket 1 subtract the natural log of 2. Question number 8. 2 birds are flying towards their nest, which is in a tree. Relative to a fixed origin, the flight path of each bird is modelled by a straight line. In the model, the equation for the flight path of the first bird is r1 equals -152 plus lambda lots of 2a0, and the equation for the flight path of the second bird is r2 equals 4 1 3 plus mu times 0 1 -1. Lambda and mu are scalar parameters and a is a constant, and what we have to do is, well, we're given in the model the angle between the bird's flight paths is 120 degrees, and we have to determine the value of a. Well, we've got vectors r1 and r2 in component form. Now we need to find the angle between those two vectors. Well, we know that the angle between those two vectors is 120 degrees. So using the dot product, we have the cosine of 120 degrees equals, well, we've got the direction of r1, 2i plus aj, dot with the direction of r2, j minus k. And then we will divide this by the magnitude of the direction of r1, so that is 2 squared plus a squared, and then we multiply this by the magnitude of the direction of r2, 1 squared plus -1 squared square rooted. So, working out the left hand side, the cosine of 120 degrees is -1/2, and on the right hand side, I've got 2i dot with 0i, so that's 0. I've got aj dot with j, so that's just a. And then I've got 0k dot with minus k, so that's just 0. And then I will divide this by, well, 2 squared plus a squared, that's 4 plus a squared, and then I square root. 1 squared plus 1 squared, that's 2, and then I square root. So I end up with -1/2 equals 0 plus a plus 0 divided by 4 plus a squared square rooted times square root of 2. So, if we square both sides, squaring -1/2, we end up with 1/4, and squaring the right hand side, well, what we end up with is a squared divided by 2 multiplied by 4 plus a squared. So, if I multiply through by 2, 2 times 1/4, that's 1/2, and that's equal to a squared over 4 plus a squared. And so we have 4 plus a squared equals 2a squared. A squared is equal to 4. A equals plus minus 2. And because the cosine of 120 degrees is less than 0, that means A is equal to negative 2 only. Now, for part B, we have to verify that, according to the model, there is a common point on the flight paths of the two birds, and we have to find the coordinates of this common point. Well, the common point occurs when r1 equals r2, which means we've got r1 minus 152 plus lambda times 2 minus 2, 0 equals 4 minus 1, 3 plus mu times 0 minus 1, 1. Now, if I take a look at the I components, then I've got minus 1 plus 2 lambda equals 4. And from this, I can see that lambda is equal to 5 over 2. And if I take a look at the k component, then I've got 2 equals 3, rather here, I've got minus 1, minus mu, in which case mu is equal to 1. And now what we can do is check that the values of lambda and mu satisfy the j component. So if we check in the j component, we have 5 plus 5 over 2 multiplied by minus 2 equals minus 1 plus 1 multiplied by 1. So I get 0 equals 0. And because here the left hand side is equal to the right hand side, the values of lambda and mu work, which means they intersect, so there is a common point where they meet. The coordinates are 4, 0, 2. And the way we got that, I've got 4 plus 1 times 0, which is 0, minus 1 plus 1, that's 0, and 3 plus 1 times minus 1, that's 2. So that's how we got the coordinates. And then, for part C of the question, the position of the nest is modelled as being this common point, so this coordinate 402 is the coordinates of the nest. And what we have to do is, well, we've got this tree containing the nest in a park, and the ground level of the park is modelled by the plane with equation 2x minus 3y plus z equals 2, and we have to determine the shortest distance from the nest to the ground level of the park. Now, the shortest distance from some point alpha, beta, gamma from a plane n1x plus n2y plus n3z plus d equals 0 is given by this formula here. So what we can do is rewrite our equation of the plane. If we have 2x minus 3y plus z equals 2, we can rewrite this as 2x minus 3y plus z minus 2 equals 0. So in that case, we know what n1, n2, and n3 and dr. And we can use this formula here. So, to find out the shortest distance between this point and this plane, the shortest distance will equal 2 times by the 4 minus 3 times by the 0 plus 1 times by the 2 minus the 2, and then we want the magnitude of this, and then we divide this by 2 squared plus minus 3 squared plus 1 squared square rooted. And if we work out what the shortest distance is, we have the magnitude of 2 times 4 minus 3 times 0 plus 1 times 2 minus the 2 divided by the square root of 2 squared plus 3 squared plus 1 squared. So we get 2.14 given to 3 significant figures, and the units, well, we're not given any particular units, so let's just write units. Now, for part D, by considering the model, we have to comment on whether our answer to part C is reliable, giving a reason for your answer. Well, the answer is unreliable because it's unlikely that the birds fly in exactly straight lines, so the coordinates of the nest are not likely to be accurate, which means this shortest distance is not likely to be accurate. Question number 9. We are given that y equals cosh x to the n, where n is greater or equal to 5, and for the first part of part A, we have to show that d squared y over dx squared is equal to n squared times cosh x to the n minus n times n minus 1 times by cosh x to the n minus 2. So, for part A, for the first part, we begin with y equals cosh x to the n, which I'm going to write as follows. And what we need to do is find out what d squared y over dx squared is. So first thing I need to do is differentiate to find out what dy over dx is, and for this we can use the chain rule. I multiply by the power, and then I subtract 1 from the power and multiply by the differential of the bracket, which is sine hyperbolic sine x. And now what we can do is rewrite this as n times by sine x times by cosh x to the n minus 1. And now we can find out what d squared y over dx squared is using the product rule. And if we were to use the product rule, well, what we can do is let v equal sine x and u equal n times by cosh x to the n minus 1. So I've got v, which is sine x times by the derivative of n times by cosh x to the n minus 1. So that will equal well, I times by the power, so that leaves me with n times n minus 1 times by cosh x to the n minus 2 times by the derivative of cosh, which is sine. So I've got v times by u dash plus u, which is n times cosh x to the n minus 1 times by the derivative of sine x, which is cosh x. So if we tidy this up, what we have is, well, this result here, let's tidy this up first. I've got n times by cosh x to the n minus 1 times by cosh x. Well, because here the power is 1, I can add the powers, leaving me with cosh to the n x, and that's by adding n minus 1 to 1, leaving us with n. And then here I've got n times by n minus 1 times by sine squared x times by cosh to the n minus 2 x. Now, sine squared, that's the same as cosh squared minus 1. So I've got n times by cosh x to the n plus n times n minus 1 times cosh squared x minus 1, and I'm going to multiply this by cosh to the n minus 2 x. And now if I expand, what we have is n times by cosh x to the n plus n times n minus 1 times by, well, here I've got n times n minus 1 multiplied by cosh squared x times by cosh to the n minus 2 x minus cosh to the n minus 2 x. And so what we can do here is add the powers. So I've got n times by cosh n x plus n times by n minus 1 multiplied by, well, here I have 2 plus n minus 2 as my power, so that's just going to be cosh n x, and then I subtract cosh n minus 2 x. So if I now expand the brackets, I have n times by cosh n x plus n times by n minus 1 times by cosh n x, subtract n times n minus 1 times cosh n minus 2 x. Now we need to simplify this a little further. Now here, notice how I've just got an n squared cosh n to the x, so somehow I need to get that result from here, and I still have the minus n times n minus 1 times cosh n minus 2x. That's over here. So this bit stays the same, but this bit here we need to simplify even further. So I've got n cosh nx, and if I multiply n by n minus 1 and then cosh nx, I'm going to get n squared cosh nx subtract n times by cosh nx, and this bit would stay the same. So n cosh nx minus n cosh nx, this bit and this bit simplify to 0. So I've got n squared cosh nx minus n times by n minus 1 times cosh n minus 2x. And that's exactly what we wanted to show for d squared y over dx squared. Now we have to determine an expression for d4y over dx4. Well, before we do anything else, let's just rewrite this result as n squared multiplied by, and then in brackets, cosh x to the n minus n times by n minus 1 times by cosh x to the n minus 2. So what I need to do now is differentiate this, and so if we differentiate, well, d cubed y over dx cubed, that's equal to, well, if I differentiate, I times by the power, so I have n cubed, times by cosh x to the n minus 1, and then I times by the differential of the bracket, which is sin x. And then here, I first of all times by the power, so I've got n times n minus 1 times n minus 2 times by cosh x to the n minus 3, so I subtract 1 from the power, and then it times by the differential of the bracket, which is sin x. So now that we've got that, let's tidy this up a little. So I've got n cubed times the cosh x to the n minus 1 times by sin x minus n times by n minus 1 times n minus 2 times by cosh x to the n minus 3 times by sin x. Now, if I differentiate this again, well, notice how we have differentiated n times by sin x times by cosh x to the n minus 1. And that's what I have over here. And then to differentiate this, I'd have to use the product rule again. So what I'm going to do is rewrite this as n squared multiplied by n times by cosh to the n minus 1x times by sin x. And then this bit would remain the same. So what we have here then, for me to differentiate, to find d4y over dx4, I have n squared times by the derivative with respect to x of n cosh to the n minus 1x times by sin x, and then I have n times by n minus 1 times n minus 2 times the derivative with respect to x of this over here. So if I differentiate n times by cosh to the n minus 1x times by sin x, well, I've already worked out what that is. I differentiated that here, and when I differentiated, what I should end up with is this over here. So that is the result of differentiating this over here. And then I have the derivative of this, which I need to work out. So I subtract from this n times by n minus 1 times n minus 2. But then what I need to do is differentiate this result here. And I need to differentiate with respect to x using the product rule. So what I'm going to do is rewrite this. Well, I've got here, if I differentiate, I've got v, which is sin x, times by the derivative of this, which is n minus 3 times by cosh to the n minus 4 x times by the differential of cosh, which is sin. So that's using the chain rule, plus, so I've got v times by u dash plus u, which is cosh to the n minus 3 times by the derivative of sin, which is cosh. So I need to now tidy all of this up. So what I end up with then is this bit, which stays the same, then I subtract from this n times by n minus 1 times n minus 2, and then if I tidy this up, what we have is n minus 3 times by sin x times by sin x, so that is sin squared x times by cosh n minus 4x, and then here, if I add the powers, I have cosh the n minus 2, because I've got n minus 3 plus 1, so that's n minus 2 x. So that is what d4y over dx4 is. Now, hence determine the first three non-zero terms of the Maclaurin series for y, giving each coefficient in its simplest form. And when the formula book here is the formula for the Maclaurin series, I need to work out y of 0, y dash of 0, y double dash of 0, and so on and so forth. So, we begin for part B of the question with y. So if I work out what y0 is, y0 is equal to cosh 0 to the n. Now cosh of 0, that's going to equal 1. So I've got 1 to the power of n, which will equal 1. And that's true for all values of n being greater or equal to 5. Now I need to work out what dy over dx is when x is 0. So if I work out what dy over dx is, well, here is our expression for dy over dx. That's shown here. But what I need to do now is replace the x with 0, and because sine of 0 is 0, this result will always equal 0. Then for the second derivative, when x is 0, well, I know what the second derivative is equal to. That's this result here. And what I can do is replace the x with 0, and if I work out what this is, well, cosh of 0, that will equal 1. So I've got n squared times by 1 to the n, which is always 1, subtract n times by n minus 1 times by 1 to the n minus 2, which is the same as n squared minus n times n minus 1, and that's true for n being greater or equal to 5. So I've got n squared minus n squared plus n, which is just n. So this is true for n being greater or equal to 5. So I've got 1, 0, and then I've got n. So I want the first three non-zero terms, so I need to work out what d3y over dx3 is. So I know what the third derivative is. That's this result here. But I need to replace the x with 0. So I'm going to replace the x's with zeros as we see here. And because sine of 0 is 0, this result will always equal 0. And now I need to work out what the fourth derivative is when x is equal to 0. Now I know what the fourth derivative is. That's shown here. So what I need to do now is replace the x with 0, so if I work out what this is, I've got n squared multiplied by, well, here I have n squared times 1 to the n minus n times by n minus 1 times by 1 to the n minus 2, subtract n times by n minus 1 times n minus 2, and then here I have sine of 0, which is 0, and then I have cos of 0, which is 0, so here I've got 1 to the n minus 2. So I have n squared multiplied by n squared minus n times by n minus 1, subtract n times n minus 1 times n minus 2. So if we work this out, I've got n squared times by n squared minus n squared plus n subtract n times by, well, here I have n squared minus 3n plus 2. So I have n squared times by n, subtract, and if I expand along here, I have n cubed plus 3n squared minus 2n. So I've got n cubed minus n cubed plus 3n squared minus 2n, which is 3n squared minus 2n, which is the same as n times by 3n minus 2, and this is true for n being greater or equal to 5. And so what we can do now is use the Maclaurin series result here. So with the Maclaurin series, we have y equaling y0 plus y dash of when x equals 0 over 1 factorial times by x plus y double dash when x is 0 over 2 factorial times x squared plus y triple dash when x equals 0 over 3 factorial times x cubed plus the fourth derivative when x is 0 over 4 factorial times x to the 4 plus higher order terms. Now I know what each of these are, so I've got y equals 0 plus, rather, y when x is 0 is 1 plus 0 over 1 factorial times x plus, well, here the second derivative, I work that out to be n, so I'm going to add on n over 2 factorial times x squared. The third derivative, I worked that out to be 0, so I'm going to divide this by 3 factorial times x cubed, and the fourth derivative, that is n times by 3n minus 2 over 4 factorial times x to the 4 plus higher order terms. So I've got 1, 2, 3 non-zero terms, and this is 0 and this is also 0. So what I end up with then for y is 1 plus n over 2 x plus n times by 3n minus 2 over 24 x to the 4 plus higher order terms.